Hello there, this is an Algebra 2 video. It is Chapter 7, Section 3, and today we're talking about logarithms and logarithmic functions. So I want to remind you that a while back, a couple of sections ago actually, wasn't that long ago, we were talking about exponential functions. And so one of the exponential functions we have here is y equals 2 to the x. And one of the things that you might recall is that when you graph inverse functions, you can invert x and y. And so you see your x is the input, y is the output. So this is when we talked about inverse functions in a previous chapter. It just so happens that a logarithm is the inverse function to an exponential function. So where you've seen y equals 2 to the x, which I've graphed for you just again, this is the graph of y equals 2 to the x. I've also graphed y equals x because when we talked about inverse functions, we talked about how the graph should be mirror images along this line. If you don't recall, you can go back and check in a previous chapter for that. So what I've done is I've created a table of values that I use to graph the blue graph here. And we want to graph now the inverse of that. So I put here y inverse, which is basically going to be from now on the logarithmic function. And so I'm inverting the x and y coordinates to graph the inverse function, because I want you to see what a logarithmic function looks like. So instead of -3, 1/8, we're going to have 1/8, -3. Instead of -2, 1/4, you're going to have 1/4, -2. Instead of -1, 1/2, you're going to have 1/2, -1. And instead of 0, 1, 1, 0. Instead of 1, 2, 2, 1. Instead of 2, 4, 4, 2. And instead of 3, 8, 8, 3. All right? And so then if I graph these points on my lovely graph over here, 1/8 is really small. It's going to be really close to my, so right here's a -3, so -3 is down here, so I'm going to put it right about there. It's not touching the y-axis, but it's really close. 1/4 and -2, so this is about half. Then half of half is right about here. So 1/4 and then -2 is going to be right about there. 1/2 and -1, so now we're at the half part, here's -1. And then 1, 0 is going to be right here. 2, 1 is going to be right here. 4, 2, 1, 2, 3, 4, 2, right there. And then 8, 3. So here's 8 and 3 is right here, so right about there somewhere. So you're going to end up with a graph that looks like this. And it's the way it's supposed to look, because lo and behold, it is a mirror image to the blue graph, or at least more or less. Obviously I'm not perfect, but there you go. So the inverse of y equals 2 to the x can be defined as x equals 2 to the y, or basically it can be what we call a logarithmic function, or the logarithm. So we're now going to go to that little guy. So this is basically what I'm talking about. We have now a new function, and I can probably write it over here before I move on from there. We want to write that y equals log base b of x is now what this guy is. Y equals log base b of x. When you read that, it's log base b of x. Log base b of x. That's how you would read it. Log base b of x. You don't say log subscript bx. You don't try to go log x. It's y equals log base b of x. All right? So over here we want to kind of have more of a formal definition for you of what the logarithm is. So of course there's a couple of stipulations. The b value can't equal 1. So your base can never be 1, because obviously we're talking about base, like powers, like 1 to any power. 1 to any power is always going to be 1, so it doesn't really include anything where the base is 1. So we can't have b equal 1. And furthermore, the number b and x are positive. That means that they're not negative and they're not 0. Positive does not include 0. There's not an equal sign in here. This is just strictly greater than 0. It has to be positive. All right, so what we're saying here is that log base b of x equals y is true if and only if, you remember this from geometry, the double F there, if and only if b to the y equals x. This might seem confusing to you because it doesn't have any numbers in it, but basically it's this statement right here. If log base 3 of 27 equals y, which is basically logarithmic form right here, then it means that 3 to the y equals 27. In other words, if I wanted to figure out what y was, what is the value of y? That's the question, right? What is log base 3 of 27? Well, it might be easier for me to look at that if it's in exponential form, which is 3 to the y power equals 27. So it's kind of like asking 3 to what power would equal 27? We know that 3 to the 1 power is 3, and 3 to the second power is 9, so 3 to the third power would be 27. So that means that y would equal 3, okay? So in other words, 3 to what power equals 27? I like to draw this diagram because it helps a lot of people. 3 to what power is 27? Well, 3 to the third power is 27. Therefore, log base 3 of 27 equals 3. So logarithms are not that complicated, but it is kind of using your brain working backwards from exponentials. So it can get kind of tricky, but once you get the hang of it, it's actually not that bad. All right, so we want to try some examples just to get your feet wet here. We're not doing anything too crazy yet. We want to write each equation in exponential form. You can see that because they both have the word log in them, they're not in exponential form. Now, right now, they're currently in logarithmic form. So remember the little pattern that I showed you a while ago? You want to go 2 to the third power equals 8, and that's true. 2 to the third power is 8. 2 times 2 is 4, and 4 times 2 is 8. So you see how that little pattern actually helps out a lot. So there, you're done. You've written it in exponential form. Exponential form is 2 to the third power equals 8. So then in this case, you would have 4 to the negative fourth power equals 1 over 256. So 4 to the negative 4 power would equal 1 over 256, which is also true because if you remember your rules of exponents, if you have a negative exponent, you can actually make that. Now, technically, I just want to be clear, the problem is done. We're done doing the problem. But I just want to show you that it's actually true like I did with that one. Because if you wanted to get rid of the negative exponent, you would have to go 1 over 4 to the fourth power. And 4 to the fourth power is, in fact, 256, because 4 times 4 is 16, and 16 times 4 is going to be 64, and so then 64 times 4 is 256. So you would, in fact, get 1 over 256. So it's actually true. We're not giving you anything that's not true. All right, so all I've done is to write it in exponential form is to do my little 4 to the negative fourth power is 1 over 256. It's that simple for you to do. Okay, so then we want to try, these are your do-it-yourself questions here on the bottom. And then we're going to go the other direction. What if we have it in exponential form and then we want to put it in logarithmic form? Okay, so again, this time we are going to say that our base is 15 because it's 15 to the third power. So it's 15, so we're going to do log base 15 of 3,375 equals 3. And you can check it with the little 15 to the third power is 3375. 15 to the third power is 3375. So therefore, log base 15 of 3,375 is 3. Same thing over here. You want to use the word log. Our base in this case is 4. So we're going to say 4, log base 4 of 2 is 1/2. And again, you can check it by going 4 to the 1/2 power is 2. 4 to the 1/2 power is 2. And that's your logarithmic form. It's that simple. So now I want you to try do-it-yourself number 2 here. And then we will move on to our next example, which is actually asking us to evaluate log base 16 of 4. So what they're asking me, in essence, is to evaluate this. So basically, log base 16 of 4 equals what? So again, the easiest thing for me to do is to put it in exponential form because logarithmic form is, too confusing. So that means 16 to what power is 4? Now we are going backwards because normally when you have a power, the number gets bigger. But this time it got smaller. So that tells me that the exponent is going to be negative. Okay? Or a fraction. So 16 to what power is going to be 4? We're going backwards. Now remember your relationship between 16 and 4. We know, for example, that the square root of 16 is 4, right? So if the square root of 16 is 4, yay for us, how can we write the square root as an exponent? We learned this before, again. So this would be 16 to the 1/2 power is 4. So basically, to evaluate this guy, log base 16 of 4 is 1/2, because 16 to the 1/2 power would equal 4. So don't forget that you could have 1/2, you could have fractional answers, and you could also have negative answers at times. All right, so now that's going to take us to our next portion of this lesson, which is graphing logarithmic functions. And you recall that we've already graphed exponential functions. I mentioned earlier that they're inverse functions of each other. So I just want to give you some general guidelines for logarithmic functions. The parent graph, f of x equals log base b of x. The domain for the function, all the x values that you can put in. As you can see from the graph, there's no x values beyond the y-axis. So basically, your x values can only be x's that are greater than 0. It doesn't even include 0. You can't plug 0 into the logarithmic function. The range, however, is all reals, because you can have negative y values and positive y values without end. The function is continuous. It is 1 to 1. There is an intercept. You remember that in the exponential case, the intercept was 0, 1. Now your intercept has inverted, as it should, and it's 1, 0. There is an asymptote. The exponential function had the x-axis as an asymptote, and now your logarithmic function has the y-axis as an asymptote, but the equation of the y-axis is x equals 0, which is an imaginary vertical line right here that it never touches nor crosses. I'm also put two different graphs here because this one represents a logarithmic function where the base is greater than 1, so greater than 1, and you'll notice that it's increasing in that case. And in this case, if the base is between 0 and, again, it's not negative, but between 0 and 1, like if the base is 1/2 or 1/3, something like that, that means that you're going to have it inverted, and it's going to be decreasing. It's still going to go through 1, 0. It's just going to change the direction of the graph a little bit. All right, so we want to come over here. And by the way, one of the points that is helpful on this graph to place is 1 over b and -1, but it's okay, you don't have to have that, it's all right. So we want to graph each function here. It says log base 5 of x. So you want to have your calculator, because sorry. I'm trying to avoid you having to do, okay, so we know that our points are going to be definitely 1, 0. One of the points that I didn't put, and I guess I should, I'm sorry, I keep changing my mind here. You definitely also want to put here that if you have 1 over b, you'll have -1 on the graph. So let me put that 1 over b and -1, and then I want to show you why that's happening. So we want to go with log base b of 1 over b equals, okay? This is what I want to show you right here. I didn't put it on there earlier, but I'm going to put it on there now. I'm going to add it to your graph. It's going to help you with our example. I'm basically putting, this is the point that I'm claiming is on the graph. It's going to be over here somewhere, okay, where -1 is right here. So this point right here would be 1 over b. But you're probably not understanding why. I mean, if I just gave you that information, you'd probably be like, what? So I want to explain to you where it's coming from. So imagine that I have the equation log base b of x, log base b of x, but in this case, x is 1 over b. And my question is, what is the y value? I'm claiming that it's -1, but why is it -1? We know that we can follow b to the question mark. B to what power is 1 over b? Well, that would be -1. For the same reason that it was earlier when I said that you had the -4, that when you have a negative exponent, you have to make that positive, you have to write it as a reciprocal 1 over b to the positive 1. So basically that is why this point is always on the graph as well. So we want to add that you have 1 over b, negative 1. And in this case, you would have 1 over b and then positive 1 in the case here because it's kind of inverted, right? Flipped over. So anyway, we are going to now move on to the actual graphing of this little guy. So let's erase this little guy, because I'm not entirely sure that's what I want to put there. But okay, so I was here. So basically what I want to do is I want to graph those points, and I want to graph it as easy as possible. So since the base is 5, that means b equals 5. Not only is the point 1, 0 on the graph, I'm going to get 1/5 because it's 1 over b and negative 1. So I'm going to graph this function very easily by putting 1, 0 right about here, and then 1/5 and negative 1. So 1/5 is 0.2, so it's like, that's 0.5, so it's put it right here, like that. And then, yeah, so that's pretty much all you can really use there. Then also, what about 5? You have to pick points that are convenient for you to graph, because 1, 2, 3, 4, 5. You don't want to pick things that are not convenient for you to graph. I'm picking the point 5 because, again, if I plug in log base 5 of 5, log base 5 of 5 is going to be 1 because 5 to the 1 power is 5. So if x is 5, over here, if x is 5, then y is 1. So those are 3 points that I can use. I don't need more than that. I've got my 1 over 5 here, my intercept here, and then 5, 1. So I can now put together this graph, and it looks like that, and it makes sense because my b value is 5 and it's greater than 1, so it should be in this shape, okay? So now when I look at this guy, the reverse of that is true because my base is now 1/3, right? So when it has a 1/3, you should see a graph that's going in the direction. So we know that we're going to have 1, 0. So I'll go ahead and put that over here. We know that we have 1 over 1/3. What happens if you take 1 over 1/3? 1 divided by 1/3 is actually 3. So we have 3 and negative 1. And then we're going to have, what if we pick 1/3 as x? That was the 3 points that you want to use, okay? You want to use the intercept that we gave you, the 1 over b, and then itself. So if the base is 1/3, what if we make x also 1/3? Then again, you're going to have log base 1/3 of 1/3, and you're still going to get 1 because 1/3 to the 1 power is 1/3. So 1/3 to the 1/3 power, 1/3 to the 1 power, so you're going to have that. Okay, so now we're going to graph this guy, and here's 1, 0, and then we're going to go 1, 2, 3, and then negative 1's down here, so we're going to have a point there. And then 1/3, 1, so 1/3 is right about here, 1. So you'll see that it naturally starts to follow this kind of a direction. All right, so just need 3 points. You want your intercept, you want the 1 over b point, and then you want itself. And then you can graph the function fairly easily. So now we want you to try this little guy, and then we will move on to transformations. Now in your book, it definitely goes over the transformations again for you, but we had them in the previous lesson, and it's the same transformations. We know that a +1 that's not within parentheses is basically going to be a vertical translation. It's going to shift the graph vertically. The -3 is going to shift it horizontally because it's inside the parentheses. And then, of course, the scalars in front are either going to make it more narrow or more stretched or more compressed. In the case of a 3, it's going to be, if the value of the A is bigger than 1, which is a 3, it's going to stretch it. But if it's less than 1, like the 1/2, it's going to compress it. All right, so I'm not going to write this on the board because we've done them enough times, but we're going to go ahead then and graph this little guy. And I just need some basic graphs. They don't have to be perfect, but they definitely should have some characteristics that are very key. So if you know what the parent graph looks like, it shouldn't be too complicated. But in this case, it says 3 log base 10 of x plus 1. So basically, this is the same thing as the log base 10 of x function, but it's going to be shifted 1 unit up, and it's going to have a stretch factor of 3. So I don't need to see a whole lot of things. It doesn't need to be crazy, but I do definitely need to see that there's a horizontal shift, a vertical shift of 1 unit. So instead of, normally you would have a point here, 1, 0, right? That's where it normally would be. But because you have this plus 1 here, it's going to shift your entire graph 1 unit up. And what I like to do is to draw that in with a dashed line so that, I can see it on my graph. Kind of like that. So now it's actually shifted. And then this kind of becomes my origin now instead of this. And then my point 1, 0 would not be here, but it would actually be here. Okay? And aside from that, the 3 means that it should be stretched a little bit more. So I'm just going to graph it like this. So it's not as tight as it normally is. That's pretty much all I'm looking for. I don't need to see that it's the exact points, but when there's a horizontal or vertical translation, I should definitely see that you moved it up or left or right, or that you moved it down. Okay, so that's enough of a graph for me. It's stretched vertically, so it's a little bigger than normal. There's no horizontal shift, but there is a vertical shift. So then for the next one, because of the 1/4 here, I know that it's not going to be going in this direction. It's going to be going in the decreasing direction. I know that because of this -3, it's going to be shifted horizontally instead of being shifted up like this one. This has no vertical shift, but it does have a horizontal shift. And the 1/2 means that instead of it being like stretched, it's going to be actually compressed. Okay, so let's graph that little guy. And this is our last example today, so that'll be good. There are 6 examples in the book, but I'm only going to do 5. So I'm sure that you'll be thrilled about that. All right, so normally we have that the y-axis is the asymptote, but because you're shifting this left or right, a -3 means you're going to the positive direction. So 1, 2, 3 now means that my asymptote is going to shift with my graph. So instead of it being the y-axis, it's now going to be x equals 3 is my asymptote now. And as far as shifting it up, so now my 0, 1, or sorry, my 1, 0 point, it's not, so now this is my origin. Okay, so my origin's not here anymore, so I need 1, 0 is going to be right about here, 1 unit over, okay? And then we know that because of the 1/2, it's going to be stretched, so it's going to be basically very much like this. It's not going to be very wide like that one was. It's going to be kind of compressed, okay? So we have our horizontal shift of 3 units. We know that it's going to be in the negative direction because of the 1/4, and the 1/2 is going to compress it, okay? So just out of curiosity, or I'm not sure, they didn't ask for this information, but the domain in this case of this function would actually be x is greater than 3, because along with the shift, the domain has changed for this graph. They didn't change for this graph because we didn't go left or right. So this is still my asymptote, so my domain is still x's that are greater than 0. But in that case, it's x's that are greater than 3. The range is still going to stay the same. It's going to be all reals, and the same is true here. So this is not an asymptote, by the way. This was just because I was shifting it 1 unit up. So I just want to be clear about that. but in this case, this is an asymptote. All right, so that is how you graph transformations of logarithmic functions. So now we'll have you try these two. Again, we don't want to be too picky about everything, but I do want to see your horizontal shift here, and in the case of B, you should have a horizontal shift and a vertical shift. Alrighty, so once you have completed this example, you will have completed your notes for this lesson, and I will see you in class, and thanks for watching.